candidate in applied physics program here at KAUST and the Vice President of Students for Sustainability. On behalf of the Office of Sustainability, under the auspices of Dr. Ana Margarita, here seated, and our Students for Sustainability group led by Ala Al-Bishaykha, would like to welcome each and every one of you to the second edition of our Sustainability Seminar Series. A full disclaimer, the program is fully organized by the Office of Sustainability. As we all know, today is Earth Day, and this year's global theme says it all. Our planets, our power, our planets. Power not just as electricity and energy, but as agency. The power of knowledge and innovation, which KAUST sits at the very center of, and the power of the choices we make here at KAUST, as championed by the Office of Sustainability. Today, we'll be walking through power. Today, when we talk about power and energy, the word transition comes to mind. Batteries sit right at the heart of that transition. They are what makes clean energy storable, portable, and possible. And very few people on this planet today are capable and better positioned to walk us through that story than our speaker today. I know this because I've listened to him talk about batteries. Professor Husam Alshareef is a full professor here at KAUST. He's also the Dean of the Physical Science and Engineering Division, who leads the Center for Renewable Energy and Storage Technologies, CREST. He's also piloting the Kingdom's energy transition drive for Vision 2030 with his enormous research. His work on nanomaterials and energy storage continue to shape the very technologies we are counting on to decarbonize our future. I've had the privilege of taking a class with him, like I mentioned earlier, and I can tell you that his ability to make complex feel intuitive is rare and genuinely inspiring. Today, it takes us on a 2,000-year journey through the history and evolution of batteries. The good people of KAUST, please join me in welcoming Professor Husam Alshareef.
Let's do test. Okay, it's working. First of all, thank you, Sherifdeen, for this very nice introduction, a very nice prelude to the topic of today. And I also thank the sustainability team, including Professor Anna, for inviting me to give this talk today. It is really my honor to be here on Earth Day, and I would like to wish everybody a happy Earth Day. And I decided for today, actually, not to give a highly technical talk. This talk is a mixture of history, a little bit of science, a little bit of storytelling. Basically, it's kind of light. And I thought it would be very good to frame it like this for a day like that. And I see many esteemed colleagues that have come to my talk. I'm very flattered. And I know many of you have to leave early, no problem. Just step up early and go to your other commitments. Okay, so the title here is about history and evolution of batteries, a 2,000-year history of human creativity and innovation, because it's really the battery business is full of creativity and innovation, as you will see. So first of all, the context, if you look at what's happening to battery, it's really mind-boggling. Okay, the batteries, particularly the lithium-ion battery development and growth has skyrocketed in the last few years due to electrification and due to transport, and the way this market is shaping up to be, it's going to be even one of the biggest markets in the world. If you look at the market size in billions of dollars right now for the battery, you see the essentially exponential growth, and we are expected to be nearly by $1 trillion by 2035, and we are just beginning. The electrification is just at the beginning. So this is going to be a huge market. And before the invention of the lithium-ion batteries, the two leading battery technologies that we all use in everyday life, the lead-acid batteries and the zinc-carbon batteries. The lead-acid batteries, the ones that are in your car, it's a $50 billion market. It's already dwarfed by just the beginning of the lithium-ion battery. So you understand how big this is. And the zinc-carbon batteries, these are the small ones we buy at Tamimi. When they run out, we throw them away. It's only a $5 billion market. So the batteries we have mostly been using up until the invention of the lithium-ion batteries already have been dwarfed by the lithium-ion battery. And today, if you look where do we find lithium-ion batteries? They're almost everywhere, to be honest with you. So they started in portable electronics, electric vehicles, home-based storage, city level grid storage, transport, and even in space. And like Sherifdeen alluded to, if you look at a lot of the analysis, there are many numbers out there by different agencies, but there's one theme that is actually common to all of these analyses, is that if you really want to meet the environmental goals and reach net zero, the most effective way to do this is actually through two components. One is to produce electricity from renewable energy like solar, wind, and so forth, and to actually electrify the transport. If you do these two things, you're going to cut roughly 75% of the CO2 emissions, which will go a long way to actually take you to net zero. So without batteries, you cannot do these two things because renewable energy is intermittent by nature. So you need storage to be able to supply electricity on a constant basis. And the battery, there's a lot of talk about fuel cells, there are alternative fuels, but make no mistake about it. The battery has proven itself as the most effective way to go from gasoline cars to really electrified transport. So batteries are actually going to either make or break the energy transition, and that's why it's important to understand their history. So where do you think the word battery come from? Yes, 100 riyal, 200 riyal. Actually, it's a weird name. Actually, the word battery comes from, a battery used to describe, before the invention of batteries, a series of similar objects that are grouped together to perform a function. And given the geopolitical situation here, I took this from Wikipedia, and you basically have an artillery battery, means an array of cannons sitting next to each other. So it's just an array of things, really. That's what the word battery means. And Benjamin Franklin, who was a politician and a scientist, used to play with the electrochemical capacitors. And he connected a few of them, 1749 over there. And in analogy with the word battery for artillery, he called them a battery of capacitors. So a battery of capacitors means a series of capacitors connected together. And since his experiment, then people started to use the word battery whenever you have a series of electrochemical cells connected together in order to provide power. So it's really an unlikely origin of the name. This is how it came, an array of things put together and so forth. How do you make a battery? Actually, each and every one of you can make a battery in their kitchen in 2 minutes. What's your favorite fruit? You cut it up, 2 metals, maybe a nail or iron, and just a copper that you yank from somewhere, and then you have a battery, actually. That's all it is. And you need an electrolyte, which is the juice that carries the ions between the 2 metals. Actually, the fruit provides ample amounts of liquid for you to have a battery. So people play game with this. So this professor at Oxford University, Saiful Islam, there was a competition at one point who can make the biggest fruit batteries. So they won, and they ended up in the Guinness World record. Okay, they put 2,923 lemons connected in series, providing nearly 2,000 volts. So that's the world's largest fruit battery. So you see, at its basic concept, it's really a very simple device. Okay. So about 2,000 years ago, there's a German archaeologist who was digging in Iraq. They found this jar, and they were confused by what this jar is all about. But they actually analyzed it. They found that it has actually 2 metals. Okay, there's an iron in here, and then another metal, which is right here, the red color. And in between, they think it was filled with kind of a acidic liquid, a vinegar, or maybe fermented grapes. Okay, and this basically is exactly what we showed on the previous slide in the fruit. You have 2 metals, okay, and between them you have some sort of liquid or medium that can conduct ions. So they think it was a copper iron battery. What did they use it for? This is just in case you're interested in the chemistry. We normally talk about half reactions and full reactions for the battery. So basically, this is what happens to the iron, what happens to the copper, and then the full reaction in the battery. If you look what they could have used it for. People believe that they were using this for electroplating, which is basically coating gold onto some objects to give them a shiny and nice color. And some of you maybe remember from high school chemistry, I used to have these problems. You know, if you put a spoon made of X metal, for example, between two metals, will it get coated or not? Something like that. So it's kind of the same principle. So again, two metals with a medium in between. Fast forward almost 2,000 years, about 245 years ago, in Italy, there was a scientist who was dissecting a frog. His name is Galvani, Luigi Galvani, between 1737 and 1798. And you see here, there's a piece of copper that he was used to fix the body of the frog. Then he had a scalpel, and you can see the scalpel right here. Okay, this is what he was using to. So suddenly what happened, he touched actually the leg of frog with the copper and saw that the leg of the frog moved, okay? And so when you do this in a battery, current flows in the battery. So he called this animal electricity. So he came up with a theory, and he said animals actually conduct electricity to generate muscle movement, which is basically the life force within the muscles. So that's his theory of what moved the frog leg. If you look at this situation and you think about the science of it, it's actually exactly the same chemistry as in the Baghdad Battery. He had copper, he had iron, and then he had two metals, and between them, he had the tissue liquid with some salt in between. So essentially, he had an electrolyte and two dissimilar metals, which actually was a battery. There was an Italian guy who didn't believe him. He said, you don't need a dead animal to generate electricity. Actually, what you need is just two different metals, and you need to put in between them this medium, okay, that can usually liquid that can carry the ions through. And he proved this point by combining copper and zinc, two dissimilar metals, in what is called the Volta pile. And truly, this is the first electric battery, because it was a well thought out experiment where he combined metals that have different reduction or oxidation potential, and was able to generate about 1 volt. So this is one trivia. I have to acknowledge ChatGPT here. So I asked ChatGPT, how can I make this talk a little bit more entertaining, okay? So they suggested this. Before we had multimeters and voltmeters, how do you think Volta checked if the battery was working? What did he do? That would be it was easier way. He licked it. Okay. So if you lick it, you feel a tingle, okay? So that's how he did it. Don't try this at home, okay? Okay. Fast forward about 165 years ago, a Frenchman known as Gaston Planté developed in 1859 what is known as the first rechargeable battery. So the battery I showed you before, at some point you consume the metals and stops working. You cannot recharge it because there are reactions that form on the surface of the metal, and the metal oxidizes. But this battery that this gentleman developed, which uses lead and lead oxide as anode and cathode, was the first ever rechargeable battery. And in jargon, we say this is a secondary battery. A primary battery cannot be recharged. A secondary can be charged. And this battery exists in every vehicle, non-electric, even electric vehicle today. It's a $50 billion market. And the reason this battery is special, when you turn your car on, you need a pulse of high current, a lot of current at the beginning, okay? And this battery is very capable. We say it can deliver 30 C for people who are in the battery business. It means it can give you a large current in a very short time. So you can actually start the car with that pulse of current. It is cheap. You bought one. If you have a car and bought one, it's a few hundred riyal. And it can be recycled nearly 100%. So basically, this is a well-established business. It's expected to reach $70 billion market by 2030. And there are issues with it, of course, that it has a limited lifetime. So if you have one in your car, you probably have to change it every couple of years. It uses sulfuric acid as an electrolyte, which is highly corrosive. And lead, people worry about lead contamination, but the success in recycling this battery has been really tremendous. And I believe the lithium-ion battery will also be the same way. So about this gentleman, okay, again, this is trivia from ChatGPT. He actually didn't patent any of his inventions, and he died poor, even though his battery, even before his death, had become a big market. So he was actually focused on science papers, not green papers. So basically, if you want to make money out of your patent, you better make sure you patent it. Okay, this is the message. And the other story is that many people don't realize this. Actually, even today's electric vehicles, they still use that battery. The reason is that you cannot use the lithium-ion battery to provide this high pulse of current because it will age quickly. And secondly, usually the battery pack is running at several hundred volts. You need to reduce that voltage to a smaller voltage to be able to run some of the other electronics in the car. And doing this with the lead acid batteries has several advantages. I won't go into this into detail, but this is a surprising thing that people don't expect that you have in an electric car. Okay, about 160 years ago, this is another big success story. This is the zinc carbon battery. This is not a rechargeable battery. It was done by another Frenchman, actually, Leclanche, 1866. This is an inexpensive battery. Many of us use it in remote control and all sorts of gadgets. It's safe and it's widely available, but you cannot recharge it. It comes in different flavors. The one that is favored is a dry cell. You use a dry electrolyte, actually, and it has an energy density of about 80 watt-hour per kg. It uses zinc and graphite as anodes, and it's about a $5 billion market. And at low temperature, it tends to have lower performance. And this is the chemistry where the zinc gets oxidized and the manganese gets reduced during the discharge process. This gentleman, actually, he started this battery for a weird reason. You know, apparently in the 1800s, it was fancy to have an electric doorbell, just like we have a camera doorbell nowadays. You know, if you have a camera doorbell, it's fancy today. Back then, if you had the knocker, that was for the poor people. You know, the rich people had an electric bell. So actually, this is why he developed the battery for actually changing the door knocker from a manual mode into electric mode. Okay, about 95 years ago, another type of battery made it big. This is called the zinc silver battery, or silver oxide to be precise. The key thing about this was in 1800. The key thing about, so it was proposed by Volta in 1800, but it was really realized commercially by Andre in 1930. The key thing about this battery is that its high energy density means that it's good for lightweight and safety-centric application, because unlike lithium, zinc and silver are stable elements, so you don't have to worry about safety. The energy density compared to lead acid is so high, the weight of a similar size is about 1/6 of the lead acid battery, meaning that it's actually suitable for portable applications. It was used in pacemakers, it was used in watches, and of course, Andre demonstrated an electric car out of this one. So electric car actually was demonstrated way back then. The key disadvantage here is the cost of silver, especially today. Okay, so this battery actually was used in space. They took it to the moon on the Apollo lunar rover and the lunar module. But because it cannot be charged, actually, when they were completely discharged, they just left them as trash on the moon. They're still there. Another trivia there is that the candy connection, you know, silver, because it's soft metal, tends to form what these called dendrites, protrusions that under electric current, these protrusions come out of the anode, the silver anode, and they can short the battery. So actually, he spent a lot of time trying to find a way to suppress those, and he found a coating of cellophane, which is what we use to stuff candy with, actually was effective at reducing these dendrites. So basically, these batteries were wrapped in candy wrapper. Okay, about the same time, actually, another type of battery called zinc air, where the anode is made out of zinc, and the other side is actually just oxygen coming into the battery. It's used in today's most of hearing aids. So this battery is extremely safe because it has air and zinc, and this safety is extremely important for this application. It has a relatively high energy density. It can reach as much as 400 watt-hour kg. All metal air batteries, by the way, tend to have high energy density, and this is an active topic. So compared to the zinc, silver, and the lead acid, you see the energy density is double the zinc, silver, and several times more than the lead acid. Okay, so it is compact. So its primary, it cannot be recharged, and it's influenced by the environment. So because it's an air battery, whenever you have high humidity or low humidity, the performance tends to be modulated by this, which is inherently unstable. And then so the humidity, basically, if you have too much humidity, we say the battery is flooded and it's not working very well. And then basically, you say the battery is thirsty, you have kind of low humidity, it also affects the performance of the battery. So they need the weather to be just right for them. So they're a little bit finicky in that sense. And why we don't use them in phone, even though they have a higher energy density, is the reason is because actually it delivers the energy very slowly. And when you want to charge your phone, you want to charge it fast. This one will be always slow charging. That's why they didn't make it in the phone. Okay, about 60 years ago, this is called a sodium sulfur battery. This battery is actually suitable not for portables, it's suitable for grid scale energy storage. So it was invented actually by Ford in 1964, and it needs to run at high temperature. This is a disadvantage because it consumes energy, but in a desert environment like this one, actually it may be an advantage because you don't need to cool it. It's insensitive to the 50 or 60 degrees C we have here. And that picture over there is in Dubai. Dubai has 2 of these units installed. And so it has similar energy density to lithium, actually to early lithium-ion batteries. It's about 180 watt hour per kg. And there was prototype cars in the 60s, actually by Ford using this. But really the application for this one is strictly speaking for the grid storage. So this is another type of battery about, I'd say 50 years ago. It's called the aqueous hydrogen battery. This one basically uses nickel hydroxide as a cathode and hydrogen as an anode. Its biggest advantage is actually the cycle life. Look, it can go 30,000 cycles, you know. If you assume that's 1 cycle per day, I mean, you divide by 300, this is a long cycle life, okay? So, and its energy density is about 60 watt hour per kg. It was taken to space because of this long cycle life. It means you don't have to go to change it, you know. If you use a lithium-ion battery, for example, the cycle life is about 3,000. So this is 10 times more. But of course, it has its own disadvantages. These are some of the early models that they were used in space. And actually, one of my students who left KAUST here, Wei Chen, he has a startup based on this concept called Enervenue that he started in the US, where he changed the catalyst that people are used in this battery and were able to change to increase its energy density quite a bit. So getting closer to today, about 4 years ago, a nickel cadmium battery was developed by Jungner. And this battery, the key thing about it is that if you look at rechargeable batteries before this time, they were always bulky. The lead acid battery, very big. You know, this is for car, it's not for portable electronics. And so he was the first to really bring a truly rechargeable and stable battery that is easy to carry on. And this was what enabled some of these, you know, cameras that many of your parents maybe, if some of you are young to realize this, but we used to have this in the early 2000s. These were flooding the market with nickel cadmium. So this compact design with the high energy density allowed now for the first time a battery that can be hundreds of times charged and discharged to be portable, and then this actually revolutionized portable electronics. After this, there was several improvements to this technology, improving you know, iterations, improving its energy density, and so forth. But then another breakthrough took place. Oh, some trivia here. Okay, this is many know Thomas Edison was a great inventor. So it turns out there was a lot of back and forth between him and Jungner. So what happened is that during the times that Jungner were developing his battery, also Edison actually was developing nickel iron battery. And then when he heard about the nickel cadmium battery, he started to work on it, and he came up with design, and there was a lawsuit. So they went to court in the US, and of course, Benjamin Franklin Edison had more money and more lawyers, and because he had more money and more lawyers, were able to win the case. But Jungner's battery actually was still the better performing battery. And he used actually this battery to demonstrate a huge feat actually in terms of electric vehicles, huge milestones. In 1900, this is 1900, okay? He drove a car powered by his silver copper batteries in this case for nearly 150 kilometers, almost 93 miles on a single charge. So this is well before Tesla actually basically ventured into this business. And of course, silver is expensive, so this is one of the reasons why I did not make it. Since we are on the theme of sustainability, he was a man of many inventions, actually, a prolific inventor, and he was very interested in sustainability. So he had actually other achievements. He actually developed a method for producing cement while simultaneously extracting potash, which was vital for fertilizer from the same process. And he also has a method called the Jungner method, where he held patents for refining fuel and extracting oil from oil shale. So he was a very prolific inventor. So 40 years ago, basically about 1986, Stanford Olszynski, this gentleman basically developed another type of portable high energy density battery. This was the nickel cadmium. This was actually an advancement over Jungner's battery. And this one actually made it big in consumer electronics, industrial equipment, electric vehicles. And many of you may remember this type of phone, you know, the cordless phone in our homes. This is actually was based on that battery. This battery lasted hundreds of cycles and had double the energy density of the Jungner battery. And then this is why it took over and replaced it. Replaced basically the nickel metal hydride. This was used in some electric vehicles, for example, the Toyota Prius. This gentleman also was a prolific inventor, and he has a very funny quote. They asked him, how did you invent so many things? He said, I did not have a PhD, so I did not know what was impossible. Okay, so basically he tried every crazy thing under the sun and came up with a lot of inventions, actually. One of them, he was one of the first people to develop thin film solar, you know, flexible solar cells that they are hot still today, by the way, but he was the first pioneer to actually put solar cells not on silicon, but on flexible sheets of stainless steel. So this allows you to do conformal solar cell, you know, for architectural design or space applications. He actually also was the person who developed this CD. We used to store data on CD disk, okay? So he came up with these phase change materials that when hit with a laser, depending on the laser intensity, you can go from crystalline to amorphous state and back and forth, and the resistivity of the material will change. So the amount of current that passes through it changes. So he was able to store 1 or 0 based on this concept. And of course, he developed this nickel metal hydride battery, which is has been used extensively in the Toyota Prius. So about 30 years ago, there's another type of battery, and I see Anshi Wang in the audience here. Anshi works on redox flow battery. This battery, the concept is actually old, okay? It was proposed by Pisort in 1930s, but this Maria, actually, this is a well-known lady in this business, 1986, proposed this for grid storage. This battery has actually a significantly lower energy density than lithium-ion battery. But again, like the hydrogen battery, its claim to fame is that it has a long cycle life. So if you do the cost of ownership for a lithium-ion battery on the grid versus this battery on the grid, because of the long cycle life, it turns out that the cost of ownership may actually be, some cases, is smaller for this type of battery. It has some advantages like the independent control of power and energy. It has disadvantages that it uses it uses vanadium, with the price of which is relatively high, and it has a lower energy density. This is now takes us to 35 years ago. This is when the lithium-ion battery was invented. Okay, it was commercialized by Sony in 1991. This is, of course, today's dominant battery technologies. You saw the number I showed at the beginning, nearly $1 trillion market just by 2034, and it continues to change our lives, actually. The energy density at the 1991 was about 180, but we have since doubled this to it's about 300 right now. And if you go to some of the new battery chemistries like solid state, lithium sulfur, you can even go higher. If you go to lithium air, if we can make this work, we can actually fly on batteries. So the issue with lithium-ion batteries is that their safety and the cost of raw materials, the lithium prices, the cobalt prices, and the nickel prices are quite high. And so this is kind of a evolution of this battery in 1978. Of all companies, this happened actually at ExxonMobil. It's an oil company. They were thinking about to get in the battery business. And then this is the first battery, and actually still working today. You know, so there's one article about that a couple of years ago. They retested it. It's still working actually. The 1993. This is a Japanese chemical company, and they have actually developed different iterations of this. There's a Canadian company called Moly, 1990, and then Sony again. Of the, you know, and this is the structure of the battery. So this is the first part of this talk. I think I can summarize it here. This is basically what happened from the Baghdad Battery to today. And all these blue-colored batteries are ones that have been commercialized at scale, and all these yellow ones that are still subject of intensive research. Okay. So a lot of innovations, a lot of countries, a lot of people from different parts of the world really had input into this. This is not a one country show. This is not one nationality show. This is a true collective effort of people from around the world to make these advances. So, and this is a very nice figure where actually it shows you for all the battery technologies, really what the gravimetric energy density normalized to mass and where the volumetric energy normalized to volume. So if you are looking for an application where the size is very important, then we will worry about the volumetric energy density. You look at application where mass is important, weight is important, then you look at gravimetric energy density. And if you look at something, for example, both of them need to be important, then you have a certain types of batteries. This is basically all of the batteries that we are aware of today. Now, this basically concludes the first part. And in the second part, what I want to do is dig into the lithium-ion battery, because this is by far the dominant battery technology today. And this is going to be the battery that will be with us for a very long time to come. Its energy density is just so high. None of the other batteries really come close in what they can do in terms of affecting the way we live and realizing renewable electricity, realizing transport, and hence reducing CO2 emission and saving our planet. So lithium actually was discovered in 1817. There's a young Swedish graduate student who was studying a mineral called perlite, lithium aluminum silicon oxide over there. And what he realized that this mineral consumes more acid during neutralization than all known alkalis, like hydroxide at that time. So this was strange to them, but on further study, he and his PI, they realized that there is a new type of element there. They called it lithium, actually from a Greek word, which means a stone. Are there any Greeks in the room here? Okay. So the corresponding lead radical in the alkaline, meaning the element, actually was called lithium. And this is really the birth of the lithium. In 2018, this would have been the 200-year anniversary of this discovery. So how to isolate this lithium? Because you want element to be able to isolate the element. Many attempts were tried, but it was kind of dangerous, and not many people messed with it because it was extremely reactive, and lithium is one of the most reactive elements. So until Sir Davy, he actually adopted an electrochemical approach, which is basically to bring a substance and then use electricity to try to separate it. And when he used actually voltapile, so the first electric battery, to try from lithium carbonate in 1818, he almost succeeded. He made a big splash, in the Royal Society, but really did not completely isolate lithium. A lot of work followed, and then finally, Brand in 1821 again applied the voltapile, but this time to lithium oxide instead of lithium carbonate. And then he was able to isolate lithium and produce successfully. He calculated the molar mass to be 9.8 gram per mole. Of course, he was wrong, but that was the first ever measurement to really identify there is a new element. It's called lithium, and they identified its molar mass. So lithium at the beginning had many applications, but batteries, It was actually used in medicines. So lithium therapy, it was mood elevating, treating depression and mental disease. It was additive in food and beer and soft drinks. It was later used in metallurgy and ceramics, lubricants, and even in nuclear weapons. Many applications. It was until 1908. It was until 1908 that Thomas Edison actually used lithium hydroxide as an additive to increase the activity in his nickel iron battery, and this is the patent that he had on the process. So it took 100 years later till somebody finally actually found that lithium is one of the most powerful electrodes. If you're not a chemist, us in material science and chemistry, we have a list in all these elements and basically their oxidation or reduction potential. And there we put them on a certain scale. And usually when you want to make a battery, you want an element that likes to, let's say with a high redox potential and an element with a low, you combine them, you get a big voltage, and then you get a battery. So having lithium with the highest oxidation potential or the lowest reduction potential actually means that whatever you combine with it, you're going to get the maximum voltage out of the battery. So this was an important discovery, and people then realized that, oh, you know, instead of copper iron, maybe we do lithium iron or something like that. So basically expand the voltage of the battery because the energy density is dependent on the voltage of the battery. So the advantage that lithium offers as an anode is this low, metal has the most negative reduction potential, giving you large voltage. It's light. It's light. When you calculate the gravimetric energy density, if you use a light metal, you get a large gravimetric energy density. The lithium metal ion is small, so it diffuses inside the battery. The lithium is always moving. It's called the rocking chair battery, because the lithium is moved from anode to cathode into the electrolyte. Being small makes this mobility fast. Lithium metal can act as its own current collector. If you want higher energy density, and instead of using graphite anode, you use lithium anode, you can get significantly higher energy density. And as I mentioned, this is one of the active area of research. If you want to really realize battery base flights, you are going to need to use lithium metal. So this means that the lithium, because of this, redox potential, it is one of the most reactive elements. It reacts with almost everything. And when it does react, it forms these surface layers. There's a lot of study on them. They are complicated. You see the lithium metal right there, okay? After the electrolyte reacts with the lithium metal, you form nearly a mess over there. And people have spent many years studying this layer, and they call it the solid electrolyte interface, SEI. So you're going to hear me saying SEI. So this is the gentleman who discovered the SEI layer. And this is basically in the TEM, you see this layer right here. A very nice layer formed between the lithium metal and the electrolyte. So this layer, as it turns out, is actually crucial for the battery operation. Why? Because if you did not form this layer, the electrolyte will continue to react with the metal and consume it, and then the battery will quickly die. But by forming this layer, which turns out to be conducting of the lithium ions, but insulating for the electrons, actually is kind of like save the battery, the whole battery. Without this layer, we could not have a lithium ion battery. This is the truth. So another concept besides the SEI layer, this is one of the first concepts for lithium ion battery. There was a Nobel Prize actually in 1987 given to 3 scientists who discovered that actually that some compounds, some chemicals like crown ethers, for example, basically they attract or trap certain ions inside their cage or inside, the molecule. This is called intercalation, This is intercalation in molecules. And there are many examples of this, but by doing this, the intercalation process, you produce new properties. These properties can be reversible if you can intercalate out the ions. So this detrapping of an ion inside a molecule is what these gentlemen discovered, and they showed that the properties of the material can be significantly changed by doing this. Following that, there was a lot of work at Stanford University on this phenomena, the detrapping. It's now called intercalation, deintercalation, and that's kind of the basis of lithium-ion batteries. So these gentlemen here, what they showed is that you can actually put ions inside solids, not only molecules, inside solids, and they can migrate inside these solids. Of course, only certain types of solids will have that. For example, fluoride structure or something that has open openings inside the structure where the lithium ion, which is small, can fit. And they showed that the graphite, several types of material can actually intercalate the lithium. So this intercalation and the intercalation of the lithium inside a solid is really the basis of a charge on discharge of the lithium ion battery. You intercalate, you charge, you de-intercalate in the anode, and then you discharge. So understanding this science of intercalation, de-intercalation, the nature of the chemical bond when you have the intercalation, at what voltages, what electrolyte, was very critical concept. So the SEI layer formation, number one, the intercalation, de-intercalation chemistry and physics, number two, were fundamental to the discovery or the realization of lithium-ion battery that we use today. So this gentleman, who was one of the Nobel Prize winners of the lithium-ion battery work, he was basically working with titanium disulfide, which is a layer material. Many of you are working on 2D materials at KAUST. At least many people at KAUST are working on 2D materials. This was a 2D materials. The 2D material means it has really large openings between the sheets of materials. It is laterally large, but vertically thin. There's a lot of these galleries opening between the layers. So this gentleman showed that lithium can go in and out in this titanium disulfide at a very high mobility. And then he showed that with a voltage, he can actually take the lithium in and out. This X here is the amount of lithium you put in titanium disulfide, okay? So you're changing the composition in and out, forming a solid solution. So he showed that in 1976. And in fact, the first lithium-ion battery that I showed you earlier and said it's still working was done by him. He used lithium metal. He used as an anode. He used titanium disulfide as cathode, and he showed this. This was his contribution for which he got the Nobel Prize. Of course, this is the battery, and this is the paper I mentioned. What year was this published? A couple of years back. This is about remeasuring the lithium-ion battery, which was made in 1976. It is still working, showing that this thing is pretty much 2019. But the titanium disulfide had two disadvantages. Number one, it actually only works at 2 volts. So compared to the lithium, that means the voltage window of the battery is only 2 volts. This is considered low. Today's lithium-ion battery is around 3.7. Remember, more voltage means more capacity, means more energy density. And also, it's unstable in ambient. It can release H2S, which you know is an nasty gas. So people started to look for different materials. And this gentleman, John Goodenough, who he lived to be 100, he passed away 2 years ago at UT Austin. He said, okay, well, instead of titanium disulfide, we should move to oxides because oxides could give you, he looked at the energy band diagram, he was a physicist and realized that oxides could give you a higher voltage. So he proposed lithium cobalt oxide in 1980. This is roughly a 4-volt cathode. Actually, this is the cathode used in almost all portable electronics. If you have an iPhone, if you have an iWatch, but any of these type of materials, you are using any of these devices, you are using this material. He made many new discoveries, actually, and this is his material here, his original paper on the topic. And this is his patent and the characteristics of the battery. Of course, nowadays people dope it and cover it, mix it with things, but this is really the main contribution now. Instead of titanium disulfide, you have double the voltage, 2 to 4 volts. That was a huge advancement. After that, there was a lot of people that developed new types of cathodes, layered cathodes, and so forth to try to improve on the voltage or the energy density. And even up to today, this is still an active field. In my group, we work on cathodes with high nickel, and we work on cathodes with different dopants to try to yet improve the energy density. So these are some of the key people who worked in this field. So what are other discoveries that John Goodenough did is this lithium iron phosphate. This was a huge discovery. Why was it a huge discovery? Because cobalt and nickel are actually very expensive metals, okay? They are cobalt is even more expensive than lithium. And if you look at the reserves in the world, it's 10 times smaller than lithium. So it's a very expensive element. So he developed this material that uses iron, which is pretty cheap, and phosphorus was pretty cheap. And actually this material has taken over. Right now, most grid storage applications, are based on this material. And just Tesla alone, about 65% of their cars, as according to the latest numbers, are using this material. So this material is going to dominate the lithium-ion battery industry. It has lower energy density than some of the materials we use in portable devices, but for cars, for grid, it's just right. And people continue to improve its properties. We work on doping this with manganese. You can increase the energy density actually and do better. So the first effort at commercialization of the lithium-ion battery, actually, many companies were trying to do this. There was one company in Canada called Moly. What they did, it turns out that British Columbia and Canada have a lot of this material, moly sulfide. It looks like the titanium disulfide that Stanley Whittingham used. So they got the idea that what if we use this, we can use a material that's here available in Canada, and then we combine it with a lithium metal anode, and we can make a battery. That was their idea. And in fact, they did make the battery, and then they advertised it half the size, twice the power, because it was really higher energy density than anything that existed at that time. But they were not so lucky. What happened is that lithium metal is very reactive, okay? And after a while, they sold a bunch of those, and the fires started, things started to explode. So very quickly, they went out of business, and they went bankrupt. Basically, they rushed, did not focus on safety, and this basically led to the destruction of the company. So people said, okay, we cannot use lithium metal, it's too reactive, we need another anode, okay? So this lithium metal was shelved, and people start to look for an alternative, okay? One of the alternatives, this gentleman was a postdoc at Stanford, and now I think works in Spain, actually. He's still alive. He actually proposed a graphite, or carbon-based material. The lithium can come in and react with the carbon. There were reasons for him to choose this. It is well known that graphite has weak bonding between the layers, so the lithiums can go in between, and this material is conductive, and it's just a good choice if you could actually isolate it. When this reacts with carbon, actually you form lithium. With lithium, you form this lithium C6, and it looks like this under the optical microscope. So people start to focus on carbon, and it had a theoretical capacity of 372 milliamp hour per gram, the highest at that time. Okay, so people realized graphite can be a good host. The key thing is that how do you really store lithium in it electrochemically? People did not understand how it happens. And there are three scenarios, actually. I don't want to get too much into the science, but what you don't want, you want when the lithium is in the battery, the solvent in the electrolyte usually shields the lithium, surrounds it. You do not want the solvent to go inside the graphite because it will actually fracture. What you want is that when the solvent comes to the graphite, basically the solvent is removed and only the lithium ion go inside the graphite. See the green dots here. You don't want this scenario or this scenario. You want this scenario. So you have to come up with a way to actually remove the solvent from the lithium. And so basically there was a lot of work on this. People trying different carbon materials to show that lithium can be stored as lithium C6 in the carbon, but none of these patents actually realized it electrochemically. So still we could not use graphite in the battery. There was a Moroccan gentleman who was working in France, Rachid Yazami. He actually was the first to prepare this electrochemically, this compound lithium C6. Highly oriented graphite was used as a starting material in this particular salt and electrolyte solvent. And then he showed that if you actually do this, you can form basically this charge-discharge curve, okay? It turns out that his discharge, he was the first to show that he formed lithium C6 electrochemically, but this curve ended up being wrong, actually. The true curve is like the red one. But this gave a lot of the researchers, particularly the Japanese, an idea what to do, okay? So they started working. This is a company called Asahi Chemical, basically started to work on lithium-ion batteries. They tried every carbon under the sun. Initially, they excluded graphite because they was using polypropylene carbonate, which actually fractured the graphite. So basically, they found different carbons that work, but they could not make graphite work yet, okay? Then they continued to work and finally demonstrated the first battery using pet coke. Pet coke, if you don't know, is that if you talk to Aramco, after the refining process, they are left with millions of tons, of this material, pet coke. So they use pet coke with some purification, but not graphite. And they demonstrated this is truly the first lithium-ion battery that did not use lithium metal anode. They used a carbon anode. Of course, this was in 1983. They tried to commercialize this. They used basically LCO coated on aluminum. This is the lithium cobalt oxide that John Goodenough invented. They used petcoke anode, and they used this polypropylene carbonate. This actually electrolyte, they use it because it's liquid like at room temperature, but it's not the best one for graphite. As it turns out later, that we now know that this electrolyte that they were using is incompatible with graphite, but they did not know that at that time. So they kept dancing around the idea, trying to figure out what's going on. Actually, in the interest of time, I want to probably skip the next couple of slides. Not this one. This is very, very bad business decision. So this is, I should cover this one. So what happened is that these guys at Asahi Kasei, they got tired of it. They tried so many things, and it's really not working. So they sold the business to Sony, and they instead wanted to focus on this zinc carbon dry cell batteries, which is a $5 billion market today. And instead of a $1 trillion market, they got a $5 billion market. So they sold the business to Sony. Sony saw an opportunity that if we can make it work, we could actually have explosive growth in electronics. And they bought the business and they focused on it. And it was a big misstep for them. Sony was actually right. Then actually what happened is that Sony took over and they made a presentation here about the first commercial lithium-ion battery. At that time, it was 80 watt-hour per kg, but it did last for 1,000 cycles. And this is when they called it lithium-ion battery. So these batteries, if you look at this curve over here, compared to nickel cadmium, remember I showed you this earlier, suddenly you had a huge jump, even without graphite in the lithium-ion battery. So this transformed the market of portable electronics. It even also was the basis for using small cells, the 18650, we call them, in the Tesla cars. So I'm going to skip this. There's a little bit of science about how they stumbled over the years by using polypropylene carbonate to focus essentially at the conclusion of this. This is So people could not take the fact why graphite is not working, And then it wasn't until they start to play with the electrolyte and change polypropylene and mixing it with other things till they found a way actually to make this kind of curve. This is what you want right here. This kind of basically you needed a combination of a linear and a circular carbonate because that was easier to remove them from the lithium when the lithium arrived at the anode during the charging process. And the summary is right here. This is a Canadian gentleman. Basically, he summarized it. What he found out is that this combination of ethylene carbonate and polypropylene carbonate, this mixture was nearly ideal for the graphite and enabled the graphite to work. And this is basically was the first time that it was shown that an electrolyte that is compatible with the graphite forming this compound is realized in real life. And basically this completed the story. Basically graphite as anode, lithium cobalt oxide as cathode, and EC plus a linear carbonate as electrolyte. This is the reaction that controls the process by which this battery works. It's called the rocking chair battery. And these are the giants that actually led to discovery. So of course, we are hooked on lithium. This is a plot that shows basically the industry impact and then the market potential for many technologies. Look at lithium ion right at the top. Okay, and then we are now using it in everything, portable devices. Just for comparison's sake, in 1987, this movie called Wall Street, they had this kind of phone, okay, Motorola phone. It weighed 2.5 pounds, okay. Basically, that's their portable phone at that time. In another movie, okay, they had a Vodafone, actually, lead acid battery, 11 pounds, I remember they used to, you put it in the car, on the floor, and then you cannot carry it, it's too heavy. So lithium changed that for sure. First electric vehicle in 1897. Of course, more electric vehicles, 1966. This is, I showed you the silver zinc battery. And of course, the nickel metal hydride. It was used in many cars, including the Prius. In 2000, there's a company called AC Propulsion. They had an idea, why not use lithium-ion battery in electric car? And instead of making a big batteries, we can make many small cells, 7,000 almost, a few thousand, and put them in the car. So the T0 car, which they made here, it's a cool looking car. It's handmade from fiberglass. They only built 3 of them as proof of concept. It was the fastest race car from 3.8 seconds from 0 to 60, beating several of the well-known brands. So this caught the attention of many people, including one multimillionaire in Silicon Valley. I think you know his name. So Tesla Motor was born. These 2 people started it, Martin Eberhard. And what happened is that they founded Tesla in 2003. They were looking for potential investors. Reluctance from VCs, it's a new concept. The car industry is doing well. Why change? Then they actually found the investor from PayPal. And Elon Musk had already sold PayPal. He had some money. He joined and basically started taking over the company. So he only paid $6.3 million first to join. He brought in a lot more investment. He fired Eberhard, and he made Tesla his own. Okay, my car company. And then, of course, his net worth ballooned because of this to about 300 billion, or plus or minus 20 billion, something like that. They put 1 Tesla in space, actually. So he owns SpaceX, so he put 1 Tesla. So there's 1 Tesla up there. Okay, electric vehicle running lithium-ion battery. And finally, the Nobel Prize. So the Nobel Prize came in 2018 for these 3 gentlemen. And this took a long time, to be honest with you, because if you realize that the battery was discovered in 1991, and they got it in 2019, already by 2000, we knew this battery changed our lives. So actually, I used to run into John Goodenough into meetings before he passed away. So I asked him one time, how come it took so long for you guys to get the Nobel Prize in the lithium-ion battery? He said, it's very simple. The Nobel Committee did not like my views, or many scientists did not like my political views. So I waited for all of them to die. Then I got the Nobel Prize. So only because I outlived them, I got the Nobel Prize. Okay. So he was a very funny guy. And basically, it's not fair because, for semiconductors, for example, there were 8 Nobel Prizes, and for the cameras and the displays, many more, and lithium-ion battery, only 1. And I think this is probably, I will just end here and thank you for your attention and happy. Any questions?
All right, thank you very much, Professor Husam Alshareef, for the wonderful talk. It's been a wonderful journey back in history. And at this point, I wouldn't want to reiterate all the things he has said. That said, if we have any questions, either online or from those of us present here, please raise your hand and then we can give you the mic to ask your questions. Okay.
Thanks. I enjoyed the talk.
Okay, good.
My question is, what happened to the hydrogen fuel cell?
The hydrogen fuel cell, the efficiency cannot beat the battery. There was a point 10, 15 years ago where it was really intense competition between, the hydrogen fuel cell and the battery people, who will actually be driving the next gasoline-free vehicle. And I'm sorry for all the hydrogen people in this room, but the hydrogen fuel cell lost big time, And the reason is because of the efficiencies. Mainly, this is nearly 90 plus efficiency and now the lead acid battery, works at room temperature. You have to compress the hydrogen. You have to bring it to low temperature. There's a lot of complications and mechanical parts. The battery, not many moving parts, so the reliability. And it has been almost commoditized right now. Actually, the number of gigafactories right now, they produce much more batteries than we can consume. So it has already reached an inflection point in the price. When I started working on batteries, it was almost $1,000 per kilowatt hour. Now this LFP that I showed is nearly $40 per kilowatt hour. And some people say it will hit $10 in a few years. So I think for automobiles, at least, the hydrogen fuel cell is out. Now, for big trucks, that travel long distances, I think there's still potential that hydrogen fuel cells may still have some, or for ships, for example, they have potential. But for the automobiles, I think it's over.
Yeah. All right. Thank you for taking us through the journey, right, of the battery evolution. I think I'm gonna get more appreciation for these batteries before they go to the trash. The question is, I think at some point you mentioned about electrical cars starting in very early 1900 or so, for it.
Yeah.
So what happens back then? Why I think I heard like conspiracy theory that, the oil industry tried to kill it. Is this the reason why electrical cars didn't evolve since that point, or it was more battery issue?
Yeah, I mean, this was all happening in the US, and the US is really about a capitalist system, So then I would not be surprised if the oil industry did something back then. They're doing it today. Today the US is not interested in electric cars. They are not interested in solar. They're not interested in anything renewable. And I think this is not just because Trump wants this. I think the oil lobby is actually pushing for this. So I think this was one big factor. But the other big factor, there's something called range anxiety when you drive an electric car. You're afraid to, you go from here to Jeddah, and if you use one of these all the time, will I make it there or not? So people did not have the infrastructure. The batteries had silver there, which was kind of expensive. So there was a few factors: cost, range anxiety, maturity of technology, and for sure the oil industry.
Thanks.
Thanks, Husam, for a very nice talk. And so this talk is about the 2,000-year history and evolution of batteries. So where do you think we're heading in the next 2,000 years?
2,000 years?
Probably 20 or 200.
Well, first of all, I think, right now the battery, the electrification, for example, many countries already have banned gasoline, vehicles by, say, in Europe, for example, 2035. We already have specific years when some countries will no longer, accept gasoline-driven vehicles. And then if you look at what's happening in China, the country is also adopting the electric vehicles. So I think the answer is very easy, and even in the next 100 years, we will continue frantically to electrify transport, and we will continue to deploy renewables, especially given right now what's happening with oil and all the geopolitical uncertainties we have, and people are now worried whether they get the oil. So there's going to be a big drive where many countries will really try to go to renewables, and many countries are almost close to 100% renewables actually. Battery prices will continue to drop for sure, and then I think they will be affordable for many people. Right now, if you want to put solar in your home as an individual, it's quite expensive for many people in many countries. So that only solar farms are being adopted, but the prices will drop so much, many more middle class countries will be able to, even on the roofs of their home, to. So I expect just a continuation of this fast rate of adoption of electric vehicles. Now, to open in new markets, for example, in aviation, okay, we need disruptive technologies, because if you want to really fly, the energy densities today are not sufficient. We need 800 watt-hour per kg and maybe 1,000. So I think aviation is one new frontier, is that if we really want to do aviation by using batteries, we no longer can use today's batteries. The other thing is that if you want your car also performance improvement, now we can go, let's say, 900 kilometers on one charge, going 3,000 on one charge by, let's say, using lithium sulfur or another high energy or solid state battery. This will make progress. Another thing I think is fast charging. Already in China, people are saying even in 5 minutes, and in cold weather 10 minutes. Maybe in the future we will charge in 1 minute, and in cold weather in 5 minutes. So the improvements now are going to become a little bit more incremental, except maybe in aviation. There's a lot of room for explosive growth in there. Very good question. Sure. But see, if you look at the battery anatomy, the lithium is only one part of the story. For example, I can tell you, the cathode also is another part of the story. And there's a lot being done on cathodes, single crystal cathodes, manganese and high nickel cathodes, and high entropy cathodes. The energy density of the cathode is only around 150 milliamp hour per gram, but or graphite 372. What if somebody can make a cathode that has an energy density the same as graphite? You have a huge increase. Second thing, if you look at on the energy band diagram of the battery, where the lithium is and where the cathode is, that distance now is about 4 volt. It's actually limited by the electrolyte, not by materials. There are materials today where you can go 5.5 volts. The problem is that the electrolyte cannot take it. It will get reduced and oxidized at the anode and cathode respectively. So actually, if somebody can come up with an electrolyte that survives 5.5 voltage, I can tell you they're going to be very rich, maybe as rich as Elon Musk, because this would really change things.
Thank you. Thank you for the presentation. It was amazing. I really like that you bring like the human part, you know, it's very, very interesting. So how do you see the future of batteries in the short term, but also in the longer term? What do you think you'll be using in 5 years from now and then in 15 years from now?
Yeah, I think this is kind of related to Professor Anshi's question, is that I think the deployment, is going to just continue to climb, astronomically, especially not only new markets, but in new countries. That the electrification is not the same in every country. As the price drops, more countries will be able to afford to actually deploy battery. It used to be the worry about having a grid, renewable grid storage system is not the solar. It was actually the cost of the batteries. So I see that more adoption in the countries that already are, committed to renewables, but also new markets opening up. So I see that I believe renewables are unstoppable. If we really want to meet our climate goals, and given the statements I made earlier that the electrification and renewable electricity and electrification of the transport can be responsible for 75% of the CO2 reduction to meet our net zero goals. So I expect these to continue to grow very rapidly. Now, again, this is related to what was asked. There are disruptive things that can happen in battery technology that either can bring the cost down, or the size of the batteries down, or the cycle life of the battery. These incremental improvements will continue to happen. I'm not sure if this answers your question.
It does, but like, how do you see this problem with the batteries? Like, is it a thing that the companies are making it less shorter because they want people to buy more? And how do we solve that problem? Like, how do we take the capital, I know
what you're talking about. I always say this, if you want to engineer something good, make it last shorter. This is the business people mentality. I think I'm thinking like a scientist here. I believe that the cycle life will improve because the more people understand the mechanisms in detail. I worked in the silicon industry for 10 years, and people actually were making chips well before they understood the detailed degradation mechanism in silicon. And the more they understood it, then the lifetime of the electronics and their reliability improved. Same thing with the battery. One thing also, people are making small cells right now. There's a trend to make really large cell. So instead of making thousands of small cells, making larger cells. So I see. I don't see intentional if you're saying that people are trying to make, no, because nowadays buyers are also smarter. When a country like Saudi Arabia wants a solar battery farm, they put in upfront what the specifications they are expecting, and usually these grid levels, they're not done by individuals, it's done by countries and cities. So they upfront, the vendor has to guarantee what they're selling you. Yes.
Thank you, Husam. I enjoy very much your storytelling.
Thank you for coming here.
For the application part, it seems like the batteries are, like, say, targeting the vehicle, transportation, and consumer products. Can you also comment on, like, say, for the battery energy storage system, for the grid scale, for the renewable, the requirement for the long-term storage, as well as the requirement for fast charging or fast discharging would be different for vehicle or for consumer products?
Yeah. So a lot of these actually, to be honest with you, go to material choices. And this is why material scientists have a lot to do with batteries. So you asked 3 questions in one. I think you asked about long duration storage. Is that what you meant? You asked about fast charging. And what was the 3rd question?
One more. Is lithium ideal candidate for this for this?
Yeah, I think for the grid storage, people for a long time were talking about sodium-ion batteries replacing lithium or redox flow. But the discovery of lithium iron phosphate, and especially manganese doped lithium iron phosphate, really pushed these technologies, in my opinion, way out. Already you can get 200 watt-hour per kg with lithium iron phosphate, and the lithium is completely recycled. So you have iron, phosphorus, very cheap elements, and you can completely recycle the lithium. So the case for sodium or redox flow batteries or thermal storage even have taken a big hit in the last couple of years because of the development and the improvement of lithium iron. Lithium iron phosphate, there are different types, but some of them can do 15,000 cycles, you know. So a year is 300 cycles only. So you do the math. Actually, there's a joke. Somebody said that these LFP is so good. In the future, what will happen, instead of changing the battery for the car, you will keep the battery and change the car because they last so long. You know, this lithium iron phosphate, okay? So I think for grid, this will be the dominant material for a long time to come. There are small projects that people have demonstrated the redox flow batteries, and she knows, you know, but they really didn't take off. And even the sodium ion batteries, maybe in the cars inside the city, they don't have to go a long distance. It will be niche market for a long time to come. And for long duration storage, this is true. Lithium, if you want to store for a long time, it will be very expensive because you have to have many batteries. So people are working on, for example, thermal storage, the redox flow battery. These will complement the lithium because in a system, grid storage system, you probably need multi types of energy storage. You need for the short duration, which is most of the time. And then you may need for long duration in case countries that don't have a lot of sunshine, you have cloudy days for a few days. You may even need seasonal storage in some countries like Scandinavia. So the idea is probably these will be coupled, but it will dominantly be lithium iron phosphate.
Thank you, Sam. Thank you very much. I think it's connected pretty much what you were saying, but I was very much interested to explore the trade-offs. So we know that batteries are great for the energy transition and climate action, but we have other aspects on environmental impacts, which means access to raw materials, one of them. So do we have enough raw materials available to support the electrification, the energy transition? Second part, the recyclability and how much we can actually reduce the impact of all these batteries that go to waste. And so how can we design batteries to actually to minimize the impacts on the environment?
Okay. Yeah, this is a very good question. And I think in the beginning, what I'm mentioning, lithium cobalt oxide, people actually went away from these expensive metals for two reasons. They are hard to mine, and they're mined by children, and there's a lot of abuse around that. And they're also very expensive and not easy to recycle, to be honest with you. So there has been a shift from those. So the shift to lithium iron phosphate is partly driven by that. Get rid of the nickel, get rid of the cobalt. The talk about sodium ion battery is also driven by that because sodium is really in our bodies, you know. So sodium is a much more benign element, a much more abundant element than lithium. At the same time, I think all the data I'm seeing about the recycling of the lithium itself, which is in lithium iron phosphate, actually, I'm very optimistic that we may be able to do exactly what we did with the lead acid battery, that every lithium from the battery, we will able to get it back. But make no mistake about it, the process of making batteries is energy intensive, and it itself has CO2 emissions. And I do in my classes some calculation about, you know, give the students, okay, if you have an electric vehicle, you have a gasoline vehicle, and then, okay, you plug it at home. Is the electricity at home from renewables or from oil? So if we have electricity from oil at home, the margin actually is not big, you know. But if you actually finally deploy renewable electricity and you charge your car from renewable electricity, it definitely is a huge impact on CO2. Recycling of other components like plastic and all of that is just the same as anything else. You know, we have a lot of plastic that we are worried about recycling, battery package and all that has the same issue.
Okay. Any further question? Okay.
No problem. Our schedule till noon, right?
Thank you very much for the interesting talk. I just have a curiosity. The power packs that are by the TCP, by the chillers plant that support the supercomputer, they call it power packs. Are those batteries?
In general, if you're talking about power interruptions and having backup power, normally these are supercapacitors, not batteries. Why? Because you have to react very quickly. And the one thing that batteries are not good at is reacting very quickly. So most likely, I would say these are supercaps, which are an electrochemical device, uses carbon electrodes. And all the UPS, for example, I know in my lab, I buy UPS, they are capacitors.
Thank you.
And that's, by the way, why in electric vehicles we use the lead acid battery, because the lithium-ion battery is just not good at giving a spike of current. And if you keep asking it to do that, it will age fast.
So I have a question. You mentioned the aviation sector, but we know that the energy density of kerosene is like order of magnitude higher.
I can barely hear you. Can you? Yeah.
Thank you. So you mentioned the aviation sector, but we know that the energy density of kerosene is like order of magnitude higher than the battery that you. How is it possible to have?
I don't understand.
Yeah, I said that the energy density of kerosene is much higher.
Oh, the energy density of gasoline.
Yeah,
I understand.
So how is it possible to have like aviation based on batteries?
Well, first of all, I don't know if you know this, almost 80% of the gasoline energy goes out as heat. The efficiency is not good. Even though the energy density is much higher, you lose most of it in heat. The battery is far more efficient. Second is the CO2 emissions. So there's an environmental motivation. The sustainability of our planet is also another motivation. So you don't get all the energy in the gasoline into kinetic energy. A lot of it, most of it actually goes as heat.
Hello, Professor. Thanks for the wonderful talk. I have one quick question, how about the memory effect of the batteries? Is it good to recharge after it is completely drained, or is it going to deteriorate the battery lifetime if you recharge when it is just 50% drained?
Yeah, I understand. This is a very good question. Sometimes on my phone, actually, I said it that it doesn't charge 100%. There's a setting, its maximum is only 90 or 80%. And the reason you do that, if you think about the charge and discharge process, if you zoom in inside the battery, during the discharge, for example, the lithium is going inside the cathode. Okay, when it goes inside the cathode, it's actually stretching the layer of the material, and that puts strain on them. So the more lithium you stuff, the more strain. Okay, and the more you do that, of course, then the bonds start to break, and the material cracks, and over time with heat, it degrades and breaks down. But if you don't fully stuff it, then the stress is less. Okay, so that's the reason why it's related to kind of exhausting the electrode by fully filling it with lithium ions. That's why.
Thank you.
Any further questions? All right. In the absence of any further questions, please let's put our hands together again for Dr. Husam Alshareef.
Thank you.
So apparently that is about 2,000 years of human ingenuity in just 1 hour. Thank you very much, Prof. As we continue the batterification of the future, I would like to implore each and every one of us, let us stay charged and let us stay green. Thank you all very much, and see you at our future seminars.
Provided sandwiches.
Okay, in addition, we have additional sandwiches outside. So if you'd like to grab something, you can pick some sandwiches on your way out. Cheers.
Thank you so much.